Hi, astronomy students. Welcome to this recording for the last week, basically, in terms of materials to be covered. It's week 16. So we're going to go through what is covered in terms of topics, what kind of assignments. Those are the last assignments, including the last exam. So let me share with you the screen. So this is week 16 for you guys. We have the last exam, which is midterm 3. That is December 7th. We also have December 6th when the midterm 3 review is. The midterm review in this time is actually smaller. It has some 90 some questions, and like the previous ones, which had more than 100. So this one is kind of light in terms of the examination. So hopefully you guys will have plenty of time. As a matter of fact, the unit for week 16 is available during the spring, during the Thanksgiving break. Please, if you hear me say the spring break, correct it. There is no such a thing. We are in the spring, we are in the fall semester, so there is only Thanksgiving break. Anyway, so we have the materials ready for both of these exams. Also, there is no graded discussion for this week 16. There is week 14, which is still due December 3rd here. And here is the assignment. So please take care of that discussion because it's graded. Week 16 is not graded. Week 15, of course, is Thanksgiving week. So we're not talking about that. There is also, in addition, this quiz, which is only a 10-question quiz, is going to help you make compare, if you wish, the solar system to the rest of the universe in terms of both age and in terms of also size. It is extremely important that you turn in this assignment. Some of you did not turn in the retrograde motion of Mars, and some of you had difficulty with it. So this will make up for those grades. Take care of it. It's a timed assignment. You have 2 attempts at it. Take it, do it, so that you get a good grade in it. Hopefully that will help you with your project assignment, which is also has an importance, has a value in terms of your grade overall. So this is an important thing that you have to do. In terms of contents, we have neutron stars and black holes. Those are a continuation from previous units. Basically, the life cycle of massive stars, they end up in one of 2 scenarios, either a neutron star or a black hole, whereas small star, like our own sun, will end up in a white dwarf. So this is the conclusion, if you wish, to the life cycle of massive stars. They end up either as neutron stars or black holes, depending on how big they are to begin with. The more massive ones will end up always in a black hole. The smaller ones will end up in a neutron star. Also, we'll talk about the Milky Way and the types of stars that it has, and also the interaction of different galaxies with one another. Finally, we explore cosmology, and cosmology is the study of the evolution of the universe as a whole from its birth up to its future. So these are the topics. It's a big stuff that we have to cover. So let's get into them. Excuse me. So as I was saying, neutron stars really, and even black holes, are the end of slightly bigger than the sun, or even more massive stars than that, to their life cycle. So after they run out of, let me remind you again for the small stars like our own sun. So at some point, it will run out of hydrogen in its core. So what it does in this case, it's going to start collapsing because there is not enough nuclear reactions inside that press outward. So in this case, as it collapses, of course, the temperature increases. And when the temperature increases, the star starts to burn, in this case, helium, and in which case it's going to expand and expand very fast. It does, because nuclear reaction is very high energetic in this case. So what happened in this situation is going to expand to a much bigger size until it runs out of helium in the core. Then it's going to start to fuse the heavier elements as it's collapsing, because the temperature will increase further and further until it reaches somewhere around carbon or oxygen and nitrogen for the case of the sun. At that point, it's going to run out of fuel to fuse, and in which case it's going to collapse further until it reaches a point where the quantum degeneracy, electron degeneracy in this case, takes over, but it prevents any further collapse. due to gravity. The quantum pressure in this case is high enough to overcome that. And then in this case, what we have a white dwarf, okay? There is no more nuclear reactions in it, so it's going to cool over time, and it changes to a black dwarf, if you want to call it that way, because it's going to run out of run out of heat, and its temperature gradually decreases, and as it decreases, the color of it changes also from the visible to the infrared down to even less than that, depending on the peak temperature at that time and the peak frequency. Well, for a neutron star, for the more massive stars, in this case, they can even overcome that degeneracy because they have more stuff. As a matter of fact, as they're collapsing, they're going to fuse more and more elements, heavier and heavier elements, up until iron. At that point, there is no doing, because if you fuse iron, that is actually an endothermic reaction, in the sense that it's going to consume more energy than it produces. So there is no more outward pressure. So the star will continue collapsing at that point into a supernova. Two scenarios in this situation: either there is not enough materials, in which case the pressure on especially the protons and neutrons, they will fuse and become neutrons in addition to the existing neutrons. So now you have a star that is made up of neutrons, hence the name neutron star. Well, while it's collapsing, the angular momentum must be conserved. There is nobody spinning the star or preventing it from spinning. So the angular momentum needs to stay constant. So as it does, because the mass is getting closer and closer to one another, so the moment of inertia goes down because the mass is closer and closer, and then the angular velocity might increase. So it's going to spin super fast. As it spins, because now it's a huge magnetic field that is spinning and basically taking the charges in this spiraling motion, and that spiraling motion will cause the charges to accelerate, hence producing electric fields and magnetic field. And that signal is the one that we detect, because the star is spinning. At some point, it's pointing toward the Earth, and other times it's not pointing toward the Earth. We call this type of neutron stars pulsars. Actually, we didn't know what they were. At the beginning, we detected them until later on, we knew what they were. This is a high frequency, I mean, relatively speaking, okay, this is still in the radio range, because it's still, the time in here is not that high, okay, compared to the high frequencies that we normally talk about. But it's still extremely fast spinning, less than a second, 1/10 of a second. It goes once around its axis. So imagine that's thing, and it's spinning that fast, okay? So this is a pulsar. In extreme conditions, you might end up even with a magnetar, okay? And magnetars are tremendous magnetic field producing stars. They're still neutron stars. Well, in the extreme condition, when you have actually far more matter to begin with than what you have, you could end up with a black hole. Black hole is so massive. Remember, this is the escape velocity that we discovered when we were talking about the gravitational force. When we put the escape velocity equal to the speed of light, there is a radius below which light itself cannot escape. Hence the name of a black hole, because it will not see, you cannot see it. The only way you can see something if light is reflected or emitted from it. And this thing does not emit or reflect light, okay? At the end, we'll talk about the Hawking radiation, which is a kind of radiation, and that's how black holes actually die at the end of the day, because they will run out of energy through the Hawking radiation. Anyway, this field has a name, Schwarzschild radius, okay? After the guy who discovered it. The only way to explain this one is through relativity, because mass, I mean, quantum classical mechanics does not have a thing with it, because there is no limit to the speed in classical mechanics. But in relativity, there is a limit. And basically, this picture, you have to take it just basically as a visual to explain. The black hole is still spherical shape, okay? But this is in a 4-dimensional universe. Think of this 3-dimensional sheet of paper. And so what it does in this case, similar to this phenomenon, when you drop a ball, the more massive it is, the more dent it's going to produce in the bed. This is exactly similar to what's happening. The more mass you have in here, the more it's going to produce a dent in the space-time continuum. That is a 4-dimensional of the fabric of space-time. and if the mass exceeds if it's too big in this situation, certain limits, all the matter will fall into a singularity, into point, mathematical point, which is really kind of weird to think about it. Actually, Einstein himself refused this idea. It was part of his solutions, but he thought that this is too extreme case that nature should not have such a thing. Yeah, we discovered them. They exist, black holes, okay? They exist actually in the center of supermassive stars, supermassive galaxies. I'm sorry, in every galaxy, most of the galaxies anyway, they have supermassive black holes inside of them, like our own galaxy. It's called Sagittarius A star. That is where the black hole is, okay? So then, of course, this is the gamma factor, basically. This is the factor with which you need to make corrections to time, because time actually slows down near the black hole too, due to gravity. I know we think of it due to velocity with the special theory of relativity, but also actually with the general theory of relativity, actually gravity also causes time to slow down. Anyway, it's please read these things, because as I was saying, you will be graded on these things and you have the exam review. So take care of that, do the review also. Mention the Hawking radiation. What it is going on in this case is the following. Next to a black hole that is spinning, of course, all of it is spinning, conservation of angular momentum, so fast, matter is actually falling in it, okay? That's why it spins. As matter is falling in it, at a brief moment, very brief moment, a pair of matter and antimatter form. We have it in here talking about it. Yes, here. Okay. They form out of nothing because of the fact of the conservation of because of the Heisenberg uncertainty principle. That's basically what the Hawking radiation is. So think of it for a moment. This is what's going on. Near the event horizon, this is called the event horizon, by the way. Here, near the event horizon, a pair of electron and positron form. Bang. Okay, out of conservation of energy. Okay, just as I was explaining down in the graph. One of them falls into the into the black hole. The other one is ejected by conservation of momentum and conservation of energy. So the one that falls in the black hole, that's gone. It's done for. Okay, the one that is ejected, it's an additional. It has added some energy to the universe. Where that energy comes from? It comes from the black hole itself. So in a sense, this process, which is called Hawking radiation, emits particles all the time. And those particles, albeit it's very, very slow and small process to begin with, but over time, the black hole will run out of energy and basically will fade away. Of course, it's not going to happen in 1 billion years or 10 billion years or 100 billion years. It's going to happen over an extremely long period of time. But this is basically how black holes also lose energy. That's the only way they do. Okay, so I went into a little bit more detail than what I wanted to actually. Again, the galaxy is made up of at least 2 main stars. The one that has the uniform circular path with very low eccentricity, those are population 1 stars. And then you have the old reddish ones that have very high eccentric orbits. Those are population 3 stars. I mean, population 2 stars, those are the older ones. And there is actually 3rd generation. So this is basically a typical behavior of the stars in the galaxy. Galaxies, they do interact with one another and they feed over each other. In few, actually, our own galaxies in the process of taking, if you wish, or cannibalizing, that's the word that is used in this case, over the large and the small Magellanic Clouds. Those are 2 satellites, galaxies around the Milky Way. And actually, some studies suggest that they already went through a process once, and they're actually going to continue until all of their stars are going to be consumed by the Milky Way. Here is a word of caution about this process in here. or I should say, I mentioned before actually the fact that almost all galaxies have black holes in the middle, supermassive black holes in their middle. Magellanic Clouds apparently do not have wounds. Some of the galaxies that probably went through the process, either their black holes migrate outside or they go through the process of collision with other galaxies and leave their black holes somewhere else. But this process of galactic interactions like the M31, which is Andromeda in the future, will collide with our own galaxy. That will conclude most likely in the merger of the two supermassive black holes in the center of our own galaxy and that of Andromeda. Or there is a possibility that one of the other two basically black holes might be ejected completely out of the two, and then the mixture of the two galaxies will end up with the only one of them, which is most likely that of Andromeda, because that's the more massive one than our own. So this is a little bit about the galaxies. Cosmology in here relies on two major laws. First of all, you have Hubble Law. In this case, it tells you how fast a galaxy is moving away, because again, observations, then when Mr. Hubble looked at the galaxies that far away from us, he detected that there is a red shift, that the frequency always shifting towards the red. That means it's not red, it's shifting towards it. So if it's blue here, it's moved closer to the red, still bluish, but not as much as if it was in its position. So if the color, for example, was green, now it's closer to the red. If the color was violet, now it's closer to the red from the violet where it was. So the red shift in this case can only be explained if the entire universe is expanding, and it's expanding everywhere. Okay? And this is the law that gives you how fast the galaxy is receding away from our own. And interestingly enough, in here, it's proportional to this distance. The further away the galaxy, the faster it's moving away from us. This h is a constant. This is the Hubble constant. This determines the age of the universe, actually. And here is a scenario that from our vantage point, everything is receding away from us. So if we take this galaxy, it's 700 kilometers per second. The one on the other side also 700 kilometers per second, and we are seen to be in the center of everything. This is on a galactic scale, on a large galactic scale. As I was saying before, galaxies interact with one another and they can collide with each other, like in the case, for example, between our own galaxy and 2.5 million years away from us in here. 2.5 million light years from us is Andromeda. Actually, they are approaching one another because they're going through a collision path. But the galaxies that are very far away, if you take the entire universe as a whole, it's actually expanding, similar to this typical example that is given in here, okay? Using the rising dough as it rises, and the different points of it in every which way are moving away. Again, the further it is, the faster it's moved. This one moves more, and so on and so forth. From the vantage point of another alien civilization living on a different galaxy, everything else is receding from them, including us, okay? Including us in the Milky Way, and so on and so forth, okay? The redshift I mentioned before, this is how you measure it. They express it with a relative ratio of how much shift in the frequency versus the actual frequency. This is actually in wavelength, I should say. The difference, the shift in wavelength over the actual wavelength, the Z number in this case, will give you how fast the universe is expanding. Did we receive a value of Z equals to 12? Because that's extremely high shift, okay? It's a relative ratio in this case. This is where the frequency is. This is the shift is 12 times as much as the actual frequency. So this is a big number. Of course, the observation detected as far as 11.1. This is a very, very far away. Actually, the color of the galaxy looks reddish now because of the wavelength shifted so much toward the red, okay? Again, this value of the phase shift will help me to determine, among other things, the relative velocity with which the stars are moving, okay, and their distances. An interesting question that results immediately on calculating the density of the universe is, are we living in a universe that is flat? Or is it closed? Or is it open, like on a saddle? Okay, that depends, of course, on the curvature of the universe. That will tell me the curvature of the universe. On flat universe, a triangle, the sum of its internal angles always add up to 180 degrees. And two parallel lines will never meet. Whereas on an open on a closed universe like this one in here, the internal sum is more than 180 degrees. Actually, you can have them as big as you want, okay? And they're still a triangle, which is kind of weird if you think about it, because we're used to the Euclidean geometry, which is a flat geometry. And the same thing is actually less than 180 degrees for a negative curvature, okay? It turns out there is a value with which you can compare things, and that is the critical density. The critical density is equating basically the potential energy with the kinetic energy of the far away receding stars. And of course, you use probably even relativity if the velocities are relativistic, and some of these velocities becomes extremely high. Then in this case, you're going to get a critical density. Depending on the ratio of the actual observed density versus the critical density, we will end up with either the universe is going to basically is in a cyclic motion, is expanding right now, but at some point it's going to start shrinking, and then the process will continue because there is enough force of gravity, gravitational force in this case, will be enough to slow it down at some point and overcome basically the kinetic energy, and then starts to bring it to an extremely high temperature, and then again it's going to expand. Basically, that's what the theory is, some sort of an oscillating universe. Another possibility, if this ratio, which is the value of omega, I'm sorry, is greater than 1, in this case, the kinetic energy is bigger than the potential energy. So in this case, there is not enough gravity, not enough matter to slow down the universe. So in this case, the universe will expand forever at an accelerating rate, actually, okay? Not necessarily, I'm sorry, because now we know it's accelerating, but I'm just anticipating what we know today. But the point being in here is that it's going to continue expanding. Now, if the ratio is exactly 1, we are at the critical value, the universe will continue to expand, but critically, okay? This is what we're observing, apparently. We're observing the value of the density to, this depends, of course, on our measurements of rho, okay? We know, because we know what rho c is, it's a constant, okay? So right now we're finding as if the value of rho and rho c are exactly the same, which is an extremely odd thing, okay? But this is, as I was saying, there is new observations in the 1990s where we found actually the universe is going through a second Big Bang, if you wish. It's accelerating even at a higher rate than what we know of. In terms of the evolution of the universe, basically, and its fate, the universe, if you look at this curve in here, and I know this recording is getting a little bit longer than what I want, there is a temperature. The universe temperature right now is around 2.75 or 2.74 Kelvin, which cooled down from 10 to the power 32. That is 10 followed by 32 zeros from the moment of the Big Bang, or just around that moment, and until a temperature that is below 3 Kelvin. Extremely cold. 3 Kelvin is just above the freezing, just above the zero, absolute zero, okay? Which you can never reach, really, no matter what, okay? So this is basically where we are right now, okay? In terms of time, we are at almost 14 billion years. We are at 13.74. That's how old the universe is in terms of its age. But there is a word of caution. I really want you to read about this one in here, because there is the observable universe, there is the actual universe, which could extend far beyond, okay? In terms of the forces, actually, that's actually a better scenario to explain what's going on, is that the universe, in terms of the grand unifying theories, is that at this point we see 3 forces: gravity, which is extremely weak, and then you have the weak force, the weak nuclear force, and then you have the electromagnetic force and the strong nuclear force. Those are in terms of their, if you increase the temperature at some point, it looks like both the electromagnetic force and the weak force, they were once one force. So the theory right now predicts that these two also were unified at around 10 to the negative 30 seconds, when the temperature was extremely high, of the order of 10 to the power 26, probably 27 Kelvin. Even further than that, the force of gravity was unified with them. This is a fuzzy area. We don't know much about this one, even in terms of physics. We don't have good physics to describe what's going on in here. So this is what happened in the universe. it's immediately after the Big Bang, there was a, 10 to the negative 33 seconds after the Big Bang, the universe starts to expand in an inflation. If we don't account for the inflation, we cannot understand what's going on with it. The universe cooled down. As it cooled down, it allowed basically for the protons and neutrons to form from the quarks, because initially it was all quarks and basically leptons and different subnuclear matter. But then you have the protons and neutrons that forms and electrons. For some reason, at some point, there was a cancellation of all of the antimatter, and we were left with a slight excess. 1 for every 1 billion particles was an extra matter. So antimatter for some reason disappeared, including anti-electrons and anti-protons, okay? And the temperature cooled down around 3 minutes, then we start to form helium. And the temperature was high enough for the helium to form through the process that we discovered actually when we talked about the chain reaction, because at that time, temperature in the core of the stars. So this is a typical behavior where actually helium formed. These models that we use predict about 24% of the initial matter that was in the universe was helium, and the rest was hydrogen. And it's really exactly what we see actually in the observations today. So this is a good descriptor. This is actually good enough. So after that, the temperature starts to cool down further and further. Around 300 or 400,000 years after that, the temperature cooled just enough for light to start to escape from the universe, because remember, photons were so trapped inside that, basically inside that extreme high temperatures that even photons could not escape. That is when light started to escape. So the further we can see with our technology, up to 380,000 to probably 400,000 light years immediately after the Big Bang. And that is a long time. But then after that, clouds started to come together, and then stars start to form as they exploded. They basically formed different galaxies and all kinds of phenomena, and we are here right now. So this is in a nutshell how we got in here in terms of the universe. What are we going to end up with? It depends, as I was saying in here, about the density. Okay, the recalibration of the density. Okay, we could end up in one of these 3 scenarios, what happened to the universe. An interesting point in here, in terms of the flatness of the universe, if you take a balloon, for example, and start blowing on it, the surface initially is more curved, and as you blow, is going to be less and less curved. So it looks like the expansion itself is helping us to look like we are on a flat universe. We have a density that is very close from the critical density, and that is basically the effect of this inflation. Anyway, this is basically in a nutshell the concepts that are covered in this week. So I'm hoping that you guys will go through them, understand them, and prepare yourselves for the exam. This discussion, as I should say, I'm sorry, let me fix this one. It's not week 14, actually, it's week 16. Okay. So this discussion is not graded, okay? So make sure you do that, and make sure you do this quiz to make up for grades that you missed in the projects, okay? And also do the review, and the actual exam is going to be available and unlocked actually on December 7th at 8 a.m. And you will have to the end of the day to turn it in, because actually to do December 7th. If you guys have any questions or have difficulty with any of these concepts, or the assignments, or something is not clear to you, please communicate with me. Do not let it linger with you guys. Do not let it to the last minute and they think, oh, maybe I should have asked about this one. Ask it as soon as it happens, okay? The sooner you ask, the better it's going to be, okay? Do not let it, oh, maybe I will take care of it later on. Don't postpone things. Please do communicate, and hopefully we can do things either via messaging through Canvas, or email, or we even can go live and basically discuss these things together. And maybe it can benefit everybody else. I will send either a message or recording for the rest of the class. Thank you.